So first chapter is about functions and limits. So, but first, so let's do first examples of functions. So have you ever heard about functions? I guess so. Do you want to give some examples? Does somebody know an example of a function?
A linear function?
A linear function, good. So a linear function is, for example, let's give an example. F of x equals, let's say 3x. This is a linear function. So I can give you some stuff. I don't think you know that, but if you want to give a more general definition of a linear function, is for two real numbers, x and y, fx plus y equals f of x plus f of y. And if lambda is a Greek letter, but you can, it's just, so lambda represents here another number, f of lambda x equals lambda f of x. This is a function f that satisfies these 2 points is called a linear function. And you can see that this function is a linear function. If I want to give a representation of it, let's do in yellow, 1, 2, 3. So I will have hard time to represent 3x, so I will change, and I will put, let's say 1.5 x. And now, less or more, the function has this shape. If here it's x, and here it's y. So what is a function? A function is, I call it, for example, f or g or w or e, whatever I want. But the main thing is that it picks up a number, in general r, a number for r, and that each number, it associates another number. So I could say at, let's say D is a set of numbers included in R. We call it the domain of the function, and it associates at each number in D another number in R. All right. So I'm giving you a little bit more because it's free. There's you can work in more general spaces, and for example, quickly, if you continue to study math, you will see that you can work also in the bigger space, larger space than R, which is the set C of complex numbers. But here, from what the setting of this introduction, we will work on R, and the function will be defined on some subset of R. Okay, so that's the definition of a function. So of course, so have you another example of a function? So if not, it's not a big deal. I thought about some examples. I will give you some others. So let's say the A is f of x equals ax, with A belong to R. So this is a linear function, yes. Let's try to connect that with real things, or more to other things. So for example, I can also call f of r equals pi r squared. So this is a function, and here I will say that f is from positive numbers and 0, and we say into r, even though this is always positive. So what's that? So you know that's the area of a circle of radius r. So now if my radius changes, my surface changes, and that's the formula. This is not a linear function, right? Because it doesn't satisfy the two conditions that I gave. And essentially, you have here a square, and this implies that's not a linear function. Let's give more examples. For example, the function that at each day, I just take an example from that we all heard about this recent years, the number of positive cases, tested positive cases daily. This is a function. So let's say the first day we found the first case of COVID-19. So COVID-19 cases. Then you have day 2, day 3, day 4, and then you have each day this kind of numbers, and this is a function. So we all saw these curves about daily cases in the news. So that's a function. But actually, if I took this representation, is f from not from r but from n and into n. Another classical example. So I received a letter. You receive from time to time a letter from census, and so the number of populations in Orlando, in Union City, or in New York City, each year is also a function. So, or let's say 2019, 2020, 2021, and the number of a population, or Paris, or Le Havre, whatever, then you have the population. Okay, so now I'm trying to give you some also real applications. You can also, for example, measure the electrical activity in the brain. And what they do, for example, the most well-known, you have also the fMRI, but an easy stuff to do, quite easy stuff, it's to record an EEG, so electrical encephalogram. And what they do is they put some electrodes in your skull, and they measure a voltage at each electrode, and this gives you a signal like this, let's say. So this is a function too. So this is the time, and for example, this is one electrode of an EEG, which usually has 30 to 64 electrons in it. Okay, so I will basically stop with examples just so now for a more mathematical way. So the expression is given for example, x squared, f of x equals 3x squared plus 2x. So now, if I choose 2, for example, with this function f of 2 is 4, with this function f of 2 is 12 plus 4, 16. And I can also do, for example, f of x equals 1 divided by x. So f of 2 is 1/2, f of 4 is 1/4, and so on and so forth. We will come back with this function right now for the introduction of limits, but I wanted also to talk about the representation. And so this is my two representations. So for example, I represented f of x equals 1.5x, 1, 2, 3, 1, 2. So 1.5, if I have 1, I have 1.5 here. If I have 2, I have 3. So I will have this function here. But if I have f of x equals x squared, so for 1 is 1, for minus 1 is 1, 2, for minus 2 is 4, for 2 is 4, and I have this representation here. Yeah, let's say it has more this shape. So you have a way to represent functions, and you put the x here and the y here, and you all know that. And here is the shape of the function f of x equals x squared. You can observe here that you have a symmetry. That is, you have, if I take x, this is the same thing that f of x equals f of minus x. So this is called an even function. So the function x squared is an even function because f of x equals f of minus x, and you have here a symmetry with respect to this y-axis, kind of a mirror. Okay, any questions so far? Is it easy? Is it hard? Up to now, it's just some kind of review of what's a function. All right, now let's say if I want to represent f of x equals x squared, x to the third, now f of 1 is 1, f of 2 is 8, f of minus 1 is minus 1, and f of minus 2 is minus 8. So I will have something like that. And just, this is called a knot function. You still have a symmetry, but this is symmetry with respect to the origin. And you have, in fact, f of minus x equals minus f of x. This is called a not function. Now, let's try to introduce now the limits. And what's the interest of the limits? Up to now, we don't have interest so much in limits because at each number, I have associated another number. What's the interest of the limit? So it starts with let's consider, so 3 now limits. Let's follow the plan here. An example. So let's try now 1 divided by x. So as I said, so f of 1 is equal to what? If f of x is 1 divided by x, f of 1 is what? So f of 1 is 1. F of 2 is 1 divided by 2. What about f of a half? What's the value of that? Does somebody know? Let's pick up a name, Leslie. You know what's f of? Yeah, great, thank you. All right, let's and f of 1/10. So Leslie said f of 1/2 is 2. That's right. F of 1/10 is 10. Thank you. All right. F of 1 divided by 1 million. 1 million is 10 to the power 6. Does somebody can tell that? Yes. So now I will write that. The limit. So you all know that you can divide by 0, right? You know that. So now I will write limit when x converges to 0. I will just put a plus here. I will say what's the meaning of that, of 1x. Can somebody take a guess? Let's say you can put on the chat. So let's say from the beginning. So no, BB, it's me. So, Sophia, can you put something on the chat if you want to? Stephanie, can you have some guess about this expression? So I started with 1 divided by a half, and Leslie told it's 2. 1 divided by 1/10. 1/10 is 0.1. She said 10. She's right. Then 1 divided by 1 million. It's 1 million. I can say f of 1 divided by 1 billion. It will be 1 billion. So as I approach 0, what is my f of x? As x approaches 0, what approaches f of x? Sherlyn, Pearl. So Leslie gave all the answers. So it approaches u. I don't know what's u. No, it's more simple than that. The more, so for my f of x equals 1 divided by x, you said 1 divided by f of So 1 divided by 1 million is 1, 2, 3, 4, 5 is that, and the image is, it's a big number. Hope you have that in dollars, it's good. So you see, as the smaller here it becomes, I don't know, 3, 6, 9, 11, 12, then I will have a lot of zeros, okay? So in fact, the response here is what is infinity. This has a precise definition, but I don't want to give it right now, okay? This is a limit. You cannot divide by 0, but you know that as you approach 0 with positive numbers, the image becomes larger and larger and larger. So if I wanted to represent that with a function here, so I know 1 divided by 1 is 1, it will have this aspect. So when x goes to 0 by the positive numbers, f of x goes to infinity, because you can give a bound. You will be larger than any number. Fix any number. If x is small enough and positive, f of x will be larger than the number that you choose. If you chose 10 billions, if I can find a number such that for every smaller number, f will be larger than 3 billions. Okay, on the other side, I can also say that limit as x goes to plus infinity of f of x equals 0, and I can add a plus. Here, plus means positive numbers. Okay, so I could replace by x positive and x goes to 0. Is there any questions with that? Oh, Sherlyn gave an answer, but I didn't see in the chat. Oh, I see. So f of 1 divided by, yeah. So what you said, that was good. Yeah, what said, I guess now Sherlyn, and now I understand the answer of Leslie, was f of 1 divided by 1 divided by x equals x. Okay. Yeah. So yeah. But the point that I wanted to emphasize that the smaller here x, the smaller x, the larger f of x. When f equals 1 divided by x. Is there any question? Okay. So I can give you another representation. Let's say f of x is, let's say, is 0 if x is less than 1, and it's 1 if x is greater or equal to 1. In fact, this is called the Heaviside function. It's useful in physics. Yeah, there's various applications from that. now, if I have this function, if I represent it, let's say in red again, actually, so heavy side, I can put 0. I could put 0 here too. That's the more first thing that we do. So if I do that now, so my function is 0, but when I get to 0, it becomes 1, and for 0 it equals 1. So in this case, I can say that the limit when x goes to 0 and x is negative of f of x, this is what? So when x approaches 0, on the left side, I can see here that the limit is 0 because it's constant. If I pick up any number in the left and any negative number, I choose f of x, it will be always 0. And so will be the limit. But if now I do limit when x goes to 0, on the right side of f of x is 1. Hi, Ines. So yeah, I think Ines comes from Mexico. So welcome. We are finishing, but we're good to 15 minutes. So we're doing some basic examples of limits. Thank you to come, because I know it's quite early in, where you are. Okay, so any questions so far? All right, so now we will try to do 3 things within the 15 minutes that are remaining. Please, if you have questions, just interrupt me. If not, so I will give you the formal definition of the limit. I already gave you that. Then I will give you the precise or rigorous definition from that. Actually, a person who worked a lot on that is Cauchy, who is a French guy. On this definition, you will see that. I will comment on that, and we'll try to end this lecture by a text from a book who speaks about the beginning of calculus, and with a story from Isaac Newton, who is known for his work on physics. All right, so from the examples that we discussed today, what is a limit? So a limit is, I try to characterize the behavior of a function when x becomes closer and closer to a number or infinity. So we saw the example of the function 1 divided by x. I can also write or give the representation of, I will choose f of x equals, let's say, 1 divided by x if x is positive, and minus 1 divided by x if x is negative. Okay, and I don't define x at 0. Okay, it's my right. My function f is defined, so I can write that df is r, but I take out the 0 of the numbers. Okay, and if I represent that, so I represent it in red, so I keep my red here. This is the shape of my function f. And as we discussed before, now I can write in this case that the limit when x goes to 0, and I forbid x to be 0, I could write that f of x equals plus infinity. So what's the definition, or so we say that we write limit when x converges to a of f of x equals L, means the limit of f of x as x approaches a is L. So L can be plus infinity. So we add some symbols to the numbers. We add plus infinity and minus infinity. So I jump to now the rigorous, precise definition. So an open interval, what is an open interval? Here it's an open interval of R is defined by two numbers, a and b, with b larger than a, and I choose here parentheses to say that I exclude a and b. This is an open interval that contains all the numbers that are between a and b. So let's say that f is defined on an interval AB, and it takes values on R. And so we say that let's C belongs to AB. So we say that F admits L as limit when X approaches C. So C might or not, might be or not be in the domain of the definition. So F is defined on AB, and maybe on C it's not. And then we say that F admits L as limit when X approaches C, if, and so in this case, I don't include the case L equals plus infinity, and neither I include C. We could work on that, but I don't have time to do it right now. So if for all number epsilon, so epsilon here is a number that is supposed to be small to be relevant. So if for all epsilon positive, there exists a number mu such that if I can ensure that x minus c is less than mu, this implies that f of x minus L is less than epsilon. So here, this is the absolute value, and it represents the distance, okay? So what does it mean? It means that for any distance, I can choose my distance as small as I want. I can find a number that ensures that if my distance between x and c is small enough, the distance between f of x and L is epsilon. And this is a rigorous limit of that. Maybe you will find it some weird, some bizarre things to introduce this kind of complicated things, but later, if you want to give proofs, it's very useful to introduce this kind of rigorous stuff, which was not present in the early definition of limits and came later with the works and contributions, for example, of Cauchy. I let you with that. I will put some assignments to do. I will send you an email today or tomorrow with assignments. Try to work on it. It will be kind of a big assignment. You don't have to do everything, but try to do some part of it. Try to do some research on it. Try to do something, and the next time we'll start with questions. So before ending the session, I will just want to read some part of the book, Early Transcendentals, which I have here. So let's